Alright, so we're going to be talking about simple harmonic motion, but how it applies to a previous topic that we've covered, which is conservation of energy. So, um, I think it would be easier for me to draw a diagram of how this works. So, let's say we have a mass um, right here. So, like we have a frictionless floor with a spring, and then it's stretched back like some distance, right? And then let's say this right here is equilibrium position. So it's stretched back all the way it can be possibly stretched back, and this would be our amplitude, right? Because it can't go any farther than this because it will go back to negative to the negative amplitude right here, and it's gonna realize that it's way too far off from the the position, and it's going to go, and the restoring force, which is the spring, is going to push it back to the equilibrium position, but it's going to overshoot again, and so on and so forth. So what we can do is we can use conservation of energy to describe the total energy in the system. So you know that there's two types of energy. So there's in the total energy. So let's say uh, sigma E. So it's comprised of the kinetic energy and the potential energy. And then the potential energy is just 1/2 mv squared. But the thing is, there's two types of potential energies that we have covered. So there's the potential energy of elastic, so that's 1/2 kx squared. And then there's elastic, not elastic, then there's gravitational potential energy, and that's mgh. The thing is, as long as it's on the same level vertically, meaning that it doesn't go up or down, just left and right, then we don't need to regard um, gravitational potential energy. But we see that it's on a spring, meaning, and it has some spring constant k, and the variable, the position always changes. It's never constant because it's oscillating back and forth. Thus, in this case, the total energy is 1/2 mv squared plus 1/2 kx squared. And this applies for any point on on from negative a to a, and a meaning the amplitude, which is the maximum displacement it can go before the restoring force pushes it in the opposite direction. All right. So let's say we're given the like let's say we're given a v value, right? Let's say like v, like we're given vo, or not vo, more like v max. Say if we're given the maximum velocity, and we're supposed to find amplitude, or the maximum displacement. So given, and then find max, x max. So basically, when the velocity is at its maximum is when the kinetic energy is at its maximum. because, and that would just be at the equilibrium position, correct? So like, let's get a number line here. So 0, negative A, and then A. This is where kinetic energy is at the max, right? Because it is at equilibrium position, so the x value is 0, making have 0 potential energy. And because energy is conserved, all that energy is transferred to kinetic energy. And you could say the same thing for this. This is when the potential energy is at its max, and then instantaneously the kinetic energy is 0. So 0. So this is the potential energy max. This is also the potential energy max. And it doesn't really matter because x is squared. So if even though you have a negative right here, it's not going to matter. And energy is scalar anyway, so there's no way for you to have a negative answer unless if you're dealing with work, which is the change in energy. So what we can do is, given V max, we can actually find X max. So we can set the maximum kinetic energy to the max potential energy, because these values will just be the same because all the energy is transferred to one type. So we get 1/2 mv squared, and then 1/2 kx max squared, which would just be 1/2 mv squared equals 1/2 k a squared, because the amplitude is just the maximum displacement, how the farthest you are from equilibrium position. And then we see that basically the 1/2s cancel out, and you get mv squared equals k a squared, and then divide both sides by m, you get v squared equals k over m a squared. But you also know that k over m is w squared. So v squared equals w squared a squared, and we get v equals wa. And this actually looks awfully familiar to how you convert linear speed to angular speed and so on and so forth, which is just v equals wr. But since there's no radial arm or anything like that, because it's not rotating, um, this is basically what we have to use, and it works, and it ends up being just fine. But I also want to give you another scenario. So let's say you are trying to let's say right now is, let's try to find V max again, but we're gonna use a different way. But so or yeah, we're gonna try to find V max. So, but we're given X max. You can actually solve this in two ways. You can do what I did earlier, which is 1/2 k a squared equals 1/2 mv squared, and then you get v equals wa. And if you're solving for amplitude, it would just be v over w. Or you could solve in this way. So remember this equation, which is x of t equals A times the cosine of Wt plus phi. And also, let's just assume that there's a given time value as well. Like, let's say at t equals 0. Or not even at t equals... I mean, yeah, you would have to be given a velocity as well. But if we're trying to find a function to find Vmax, then we can do that. So we know that v of t is just x prime of t. So let's do that. Let's take the derivative with respect to time. So we get vt equals negative a sine wt plus phi. But then you have to multiply by the inside, which is just times w. And we know that v equals w times a, so we get v of t equals negative v, and this is v max. We get, and then that's sine of wt plus phi. And then you can basically divide both sides by sine omega t plus phi, and by negative 1 as well. So you get v of t over, and let's put the negative right here. So sine of omega t plus phi equals v max. So here's another way to solve for it. And I also want to cover how to find the maximum acceleration, so A max. So if we recall from a previous concept, we know that Hooke's law is the force of the string equals negative kx. But the thing is, the variable is always changing, and because the variable is always changing, the force is always changing. Thus, there's a varying acceleration. There's a variable acceleration. Therefore, we can't find the acceleration without using either having a spring constant x value, or without using calculus. So let me show you the first way to find the max acceleration. So, and you're also given, so equals, and then you're given k, and then x, and then you're also given m. So you get negative kx equals m a max. So we get negative k over m x equals a max. And we also know that w is the square root of k over m plus or minus. So when you square that, you just get w squared equals k over m. So this is basically negative w squared. And obviously, x would have to be a in this case, the amplitude, because you'd have to have the maximum distance to get the maximum force, because this is a direct relationship. As the position increases, the force increases. So just to keep that in mind. So equals a max w squared a and I'll solve. Now I'm going to solve it a different way. So A max. And I'm going to do a similar thing to what I did with the velocity. So we have x of t equals a times the cosine of wt plus phi, and then we're going to take the derivative with respect to time. So we get vt equals um, negative v max um, times sine of omega t plus phi, and then v max is just w times a. So now we're going to take the derivative again because v prime t is just acceleration t. So we get, so I'll actually rewrite this as negative w a sine t. I mean sine of omega t plus phi. So we get a of t equals negative w a cosine omega t plus phi. Then we got to multiply by the derivative on the inside, which is w. So we get a of t equals negative w squared a cosine of wt plus phi. And we know that um, omega squared times a is a max. So a of t equals negative a max times cosine of w times, omega t times plus phi. So then we divide both sides by negative cosine omega phi, omega t time plus phi. So we get a of t over negative cosine of omega t plus phi equals a max. So yeah, either you can find the like for the v max and the a max, the max acceleration, the max velocity, you can solve them either way. It's all up to preference if you like using calculus or conservation of energy. But sometimes if you're given the time, it might be easier to find um, the derivative and then use calculus. But I will if you don't like using calculus and just want to do it algebra based, for like say like the like a velocity at a given point. So like if you're trying to find a velocity at a given point, so let's say like you're trying to find the v at like say t equals 2, and you're given, and then you're given the amplitude, and then you are given the x value at 2. Which let's just say like an x of 2, which is just x. And let's just call this v at this point. So, and we're given k, of course. So basically, we can basically do the use conservation of energy. So we can do the potential energy max equals k e at time 2, and then this might look confusing. Let me just rewrite this. The ke at time equals 2, and then plus the p at time equals 2. So we can definitely solve. We can basically derive um, the potential energy max because you're given the spring constant and the amplitude, and then we can do 1/2 mv squared, and this is at t equals 2, and then we have plus 1/2 k x squared, and this is at t equals 2, so t equals 2, t equals 2. So all we have to do is solve for this guy, the velocity at t equals 2. So I'm going to subtract the potential energy at time equals 2. So we get 1/2 k a squared equals, or no, sorry, so minus 1/2 kx squared equals 1/2 mv squared. So we can cancel out the 1/2, so we get k a squared minus kx squared equals mv squared. And I'm going to factor out the k, so we get a squared minus x squared times k equals mv squared. All right, and I'm gonna rewrite this. So k a squared minus x squared equals mv squared. And all I'm gonna do is I'm gonna divide by m, so we get k over m a times a squared minus x squared equals v squared. But we know that k over m is omega squared, so we get omega squared times a squared minus x squared, which is equal to v squared. Now we just have to take the square root. So we get omega squared times a squared minus x squared equals v squared, or v. And we can take this guy out to outside the radical. We can take the angular frequency outside the radical, so we get a squared minus x squared in here, and then that just equals the velocity. So yeah, say if you're not comfortable with say if you're not comfortable with you know using calculus to solve for to solve for velocity and such, what you can do is you can actually, like, if I didn't give you x of 2, but you have all the variables to solve it, like you're given a and such, so you get a cosine of like w times 2, and let's just and then you're given phi as well, so like you can basically plug that into here, like, and assuming w and phi can be found. So yeah.